Good day, my name is Jorge Gracia. I am from the University of Chiarcos in Spain, and I'll be presenting this work jointly with my colleagues Fäth from Goethe University, Frankfurt, Germany, and Matthias Hartung from Semalytics, Bielefeld, also in Germany. We are representing a longer list of authors that you can see here. This work has been mainly developed in the context of the Prêt-à-LLOD European project. In our paper, we describe the use of linguistic link data to support a cross-lingual transfer framework for sentiment analysis in the pharmaceutical domain. In this first part of our presentation, I'll give an introduction and overview of our approach, while my colleagues will give more details about the data transformation and data exploitation processes later on. One of the challenges that language technologies providers face in global markets is the need of adapting their dedicated solutions across different languages. Cross-lingual model transfer methods are based on the idea that NLP models already existing for a source language can be transferred to a new target language without the need of retraining them or rebuilding them from scratch when adapted to new languages. As a primary source of cross-lingual information, such approaches rely on bilingual lexical resources in order to bridge the language gap. In this context, we propose the use of resources belonging to the so-called Linguistic Link Open Data Cloud to be used as catalyzers of cross-lingual transfer of NLP models in deep learning frameworks. And we demonstrated this through an in-use application built for sentiment analysis in the pharmaceutical domain. Our assumption here is that the use of linguistic link data for cross-lingual model transfer has a number of advantages. It does not rely on proprietary formats and APIs, but on standard representation mechanisms and access means like RDF, ontologies, Sparkle, etc., which also makes combination with other link data resources easier. Also, the continuous enrichment and growth of resources in the linguistic link data cloud can lead to the potential improvement of the NLP stack, exploiting them with little or no extra effort. In particular, we are using in our approach the RDF version of the Hartung family of bilingual dictionaries. Hartung is a free open source rule-based machine translation platform that currently includes over 50 language pairs. As part of its architecture, it contains a set of bilingual dictionaries that are exploited by its translation mechanisms. In a previous effort, a subset of such a family of dictionaries was already converted into RDF a few years ago, resulting in the first version of Hartung RDF, which you can see on the left-hand side of the slide, containing 16 languages and 21 translation sets. However, as part of the work presented in this paper, we rebuilt the Hartung graph, resulting in the much larger graph that you can see on the right-hand side, with 44 languages and 53 translation sets. The semantic representation of the Hartung RDF data grounds on the Ontolex Lemon ontology. Ontolex is a factoid standard to represent lexical data in RDF for the semantic web. Not entering into many details, this slide shows the Ontolex-based representation of a translation in Hartung, from the word safety in English to seguridad in Spanish. The monolingual information, mainly parts of speech and written representation, is associated to the corresponding lexical entries as represented on the left-hand side of the figure. The part on the right represents the translation between them. To finish this introductory section, I'll give an overview of the whole pipeline that the multilingual data traverse in our system. First, the Hartung source data is taken as input and converted into RDF based on the Ontolex Lemon model. This is represented as step 1 in the figure. Then, step 2 represents the linking process, in which the Hartung lexical entries are associated to entries in the Lexinfo catalog of linguistic categories, for instance, to define that an entry is a noun or a verb in an ambiguous way with a proper URI. Both steps 1 and 2 take place within the FinTime framework that my colleague Christian will explain in a moment with more detail. Step number 3 is about the publication of the resulting Hartung RDF data as linked data, and the provision of suitable query mechanisms through a Sparkle endpoint. In the final step, the Hartung RDF data is consumed by a sentiment analysis component in a user application to support cross-lingual model transfer. Now I give the floor to Christian, who will provide more details about the first steps of this pipeline.
So, first of all, thanks to Jorge for introducing the project. In the following section, we will focus on the data transformation procedure. As Jorge has already pointed out, we employ OntoLex-Lemon for modeling the Apertium data in RDF. The transformation pipeline itself consists of the following steps. We check out the most recent edition of the Apertium XML data files. We then extract linguistic annotations such as part-of-speech tags and morphological properties as a separate resource. And after that, using XSLT transformation, we directly transform the dictionaries into an OntoLex-Lemon representation. As an additional step, we employ a SPARQL query to extract TSV data from the resulting RDF dataset. So as a result, we receive one RDF file and one TSV file per bilingual dictionary. However, since the Apertium text set is not normalized, we also aimed at consolidating linguistic annotations by mapping them to Lexinfo, which is also encouraged for use within OntoLex-Lemon. This mapping builds on the linguistic annotations we extracted in the previous step. We then manually complemented it with the corresponding Lexinfo annotations. The resulting mapping table is available on GitHub for further contributions. At the time of writing, we could identify 104 Apertium categories as part-of-speech. These have been mapped to 28 part-of-speech individuals in Lexinfo and also to 15 universal dependencies tags. The discrepancy in the amount of text stems from the Apertium's heterogeneity across dictionaries, and also a difference in granularity of the respective tag sets. In the end, this mapping table is transformed into an RDF resource and can easily be applied to the converted datasets using a SPARQL update. Our goal now was to consolidate the various transformation steps into a single pipeline. Since RDF data and SPARQL updates usually require a database engine in the background for accessing and transforming larger files specifically, and are thus not very suitable for streams of data, we employed the flexible integrated transformation and annotation engineering platform, in short FINTAN, which is also in development within the Prêt-à-LLOD project. It is designed as an extension of CONNEL RDF for CONNEL TSV, which was originally designed for CONNEL TSV corpora. It employs stream-based graph processing, which is achieved by splitting RDF datasets into logical segments, like sentences in corpora or entries in dictionaries. In order to support more types of data beyond CONNEL, loader modules can be included which take care of the initial RDF transformation, like in our case the XSLT transformation in the conversion pipeline we described before. The update modules take care of graph transformation steps using data segmentation and multi-threaded processing. In our case, we load the mapping table and apply it to one dictionary entry per thread using SPARQL. In the end, we can export the RDF data in various formats using writer modules. This includes RDF dialects like Turtle and RDF XML, but also TSV, which can be achieved by using SPARQL queries. On this slide, you can see the transformation pipeline as it would look like in FINTAN. First, we use the Apertium to RDF pipeline as a loader module. Then we update the annotations by loading the mapping table and applying a SPARQL update. So the bubble, including the updates, have two sources going into them. One is the SPARQL update and one is the mapping table. In the end, we can either export the RDF directly or apply a SPARQL query to generate a TSV export. The resulting Apertium RDF version 2 dataset includes 44 languages, 53 translation sets, and each of them with almost 30,000 entries on average. In total, we have 1.5 million entries with 1.8 million links to Lexinfo. The data itself is available on GitHub as a RDF and TSV dump, and also as a formal publication including a DOI and a SPARQL endpoint. This is the link below. And with this, I hand over to Matthias Hartung from Semalytics for the use case of Apertium in multilingual text analytics.
Thank you, Christian. Let me start with a brief introduction about Semalytics and our business focus. So Semalytics is a startup company based in Bielefeld, Germany, and we are working on supporting our customers from the pharmaceutical industry in fostering patient centricity in medical drug development by providing AI-driven text analytic solutions on real-world data from various textual sources. As pharma is a global industry, we regularly face the challenge in our customer projects to deploy text analytics or NLP models across various languages. One of our approaches to address this challenge is based on a transfer learning architecture which exploits LLOD resources in order to avoid dedicated task-specific annotation needs in the target language of interest. More precisely, these LLOD resources we are talking about are bilingual dictionaries which are transformed into an RDF representation using the Fintan workflow that Christian has just introduced. And subsequently, these RDF representations are fed into a multilingual NLP component within Pharos, which is our commercial real-world data platform at Semalytics. As it is based on cross-lingual transfer learning, this process can, in principle, be rolled out for various NLP tasks and languages. We demonstrated here for a sentiment analysis model that is projected from English to Spanish. The overall architecture of the transfer workflow is as follows. Assume we have an input text in a source language, English in this case, and corresponding word embeddings from which we can compute some document-level aggregation. Using task-specific supervision in the source language, we can train a projection matrix that renders the input embeddings particularly informative for the sentiment analysis task. So far, this is a purely monolingual setting, but we can make use of bilingual dictionaries from the LLOD cloud, as you can see in the upper right corner of the slide, in order to project these embeddings into the target language. This projection capitalizes on a joint training objective that minimizes, on the one hand, the task-specific cross-entropy loss in the source language, and on the other, the Euclidean distance between task-specific representations in a shared bilingual embedding space. Coming to the experiments, and again, as I said earlier, we focus on sentiment analysis for the language pair English-Spanish, and the bilingual lexical information that we need comes from the LLOD workflow presented earlier. Our corpus is a sample of Spanish and English sales interaction transcripts from the pharmaceutical domain, which are manually annotated with sentiment labels for training in the source language and for evaluation purposes. As a baseline for comparison, as you can see on the right hand of the slide, we apply a straightforward translation pipeline which translates Spanish documents into English and subsequently applies an existing English sentiment model on these translated documents. Here are the results for different bilingual lexicons and their combinations. We find that the LLOD resource Apertium is the most valuable source of bilingual information on its own. It benefits most from being extended by the Bing Liu resource, which is a bilingual sentiment lexicon providing complementary task-specific information. And in this combination, Apertium and Bing Liu outperform the translation baseline by a great margin of approximately 24 points in target language accuracy, without the need of any annotation efforts in the target language. To conclude, we consider this a strong case of LLOD lexical resources serving as effective catalyzers of cross-lingual transfer, either on their own or in combination with other data sources. Being flexibly applicable to various languages and tasks, this example also demonstrates the strong potential of the LLOD workflows we are developing in the Prêt-à-LLOD research project as enablers of rapid model transfer in real-world scenarios. Thank you very much for your interest and your attention.